Kamailio and taking the time to come to this event. I'll let you say more about it. The floor is yours.
Thanks for the opportunity. So in this brief presentation, I wanted to talk a little bit about troubleshooting media negotiation in WebRTC environments. First of all, a little bit about Signalwire, who I'm representing today. So Signalwire comes from the creators of FreeSWITCH and has become a reference point, and it basically built on top of FreeSWITCH what can be called the CPaaS. And the vision that is now being presented is called PUC, Programmable Unified Communications. So you can build your own service on top of it, and so you can do SIP, PSTN, WebRTC from SIP or from an SDK, and there's also integration with AI agents. So you can get something very similar to what David demoed today on top of Signalwire as well. And a reference every year is the ClueCon conference in Chicago. So there you can see the latest, you can present your own projects, and it's a very good conference to attend, in my opinion. So if you can, I suggest to do it. And Signalwire continues to work on the core of FreeSWITCH. So I'm presenting a few news about it for who's interested. There was the 1.10.12 release, and there was the drop of Debian 10 and CentOS support. And a bunch of tools that reached end of life were abandoned: Jira, Confluence, Crowd, and Bamboo. And a few links for developer documentation, where to report issues, and so on. The next version, 1.10.13, is under development and could be released across ClueCon. One of the improvements was to get rid of some modules that were not really maintained, so easier for developers to embrace the project. And in terms of support for Debian, Debian 11 and 12 are officially supported until end of life, and then there's work ongoing on Debian 13. And if you have any questions, you surely can find how to reach the community. So the goals of this presentation is basically a short version of another presentation I'm preparing, and it's in general about troubleshooting WebRTC calls. It comes from the experience of a couple of years working with not only with customers, but with developers that develop their own services on top of Signalwire. And sometimes we find a little bit of friction in understanding where things go wrong when establishing WebRTC calls. Now, most of these concepts are not completely different than more traditional VoIP establishment, but there are maybe a few additional tools and caveats that may be interesting to discuss. So, obviously, even WebRTC is theoretically peer-to-peer. Typically, what happens is there is a client and a server, and the media, which is the focus of this presentation, flows through RTP streams. So this needs to be negotiated, and the core is the offer-answer model using SDP. And for free from the WebRTC and from the browsers and FreeSWITCH, we get DLS encryption of the SRTP flow. But in order to do this, this negotiation, there's need to do the exchange of SDP need to happen, and there isn't a standard way to do that. So basically, the signaling protocol was never really defined, and in some cases, SIP is still used, even though it's not the most common, and many have their own protocol. Eventually, it's just a way of transporting SDP offer and getting the answer back. One of the concepts that we try to educate our customers on is the concept of ICE candidates, because they have a key role in establishing the RTP sessions and also establishing them in a sort of timely fashion, not too slowly, and in a successful way. So other concepts that come useful in the discussion is ICE, which uses STAN as the protocol, and in some cases TURN, which is an extension of STAN. So a few things that maybe are known by most of the people, but just worth mentioning. Different ICE candidates, host, server reflexive, and relay, and then peer reflexive, which are the ones discovered dynamically. I think this one maybe is the easiest way to identify them. So a browser, which is typically behind NAT or multiple NATs, can detect its own direct candidates, which are called host candidates, and they go out through one IP and port. And again, there could be multiple levels of NAT. And they discover the server reflexive candidates. So what's the actual public IPM port that is visible by something in the public internet, like could be, say, the Signalwire platform or other services. So they can be discovered as they go out, which are the server reflexive, or there could be an active allocation of a relay session on the turn servers. And in this case, the browser discovers the so-called relay candidates, which again are communicated in this very simplistic case. So the browser is talking to FreeSWITCH through Kamailio, so it's using SIP over WebSocket. And what it does, it's communicating all the candidates for establishing the media negotiation. And this applies to both inbound and outbound calls. So it's basically the same mechanism is used whether the browser is calling the platform or the other way around, the browser is receiving a call. So in seeing in a sequence that also represents how quickly some candidates can be detected. So when the WebRTC starts gathering the candidates, the first one that are available are the local ones, which are the host ones, and they can potentially be communicated to the remote party immediately. Then the quickest discovery is the server reflexive, because it's sufficient to send a STAN binding request to a STAN server. You get a response that tells you what was the IPM port that was seen as the source of your request. So, and also this one can be communicated to the remote party, or there could be an active allocation of a relay transport. In this case, the WebRTC application talks to a turn server, allocates. If the allocation is successful, gets back a relayed address, which is also communicated. So this is an ideal scenario where it's a trickleized approach where as soon as you discover a candidate, you send it over to the other party. So if, for example, before you have discovered a relay candidate, you already have established correct bidirectional communication with the host candidates, you can just use them, you don't need to wait. What happens more commonly in some cases also with FreeSWITCH is that the candidates are gathered all together with a proper, say, timeout, and then they are all communicated at the same time to the remote party. So this is less efficient, but maybe more typical. Yes, so this is basically the difference. You can communicate them as soon as you discover them, or if you can, that's more efficient, or you need to collect them and send them in one single SDP offer or answer. And it still happens that many scenarios, like in particular call center agents, can be under NAT, and turn becomes not only an option, but sometimes a need. And also using port 443, which is a way of basically having a generic way of saying it's the most probable way out from this NAT is port 443. That proves to work typically. However, in the definition and in the implementation of WebRTC itself, the relay candidates are assigned a low priority because they represent anyway an additional hop, networking wise. And also, well, yes, there is also some price to pay for acquiring the allocation in terms of first of all, it needs to be authenticated. There's some time spent back and forth authenticating the request, and then there is bandwidth used. So you pay for the efficiency, and you get the necessary relay. So, but STAN, which is quite generic because there's the STAN protocol, and then there are the STAN servers. But in general, it's not used only for media establishment and finding the best candidates. It's also used during the call for simple verifying that the call is still up, the other party is still there responding, and the time that it takes the other party to respond is also used to measure round trip time. Yes, there could be cases beyond NAT traversal for turn. There are some cases where you may want to put your turn servers very close to the browser so that you have a shorter path between the client and the turn servers, and you possibly manage better the path between the turn servers and your media backend. So in terms of troubleshooting tools, what we try to promote with the customers and the partners is very common tools like TCP dump and the related family, Wireshark for analysis. We do have Omer and HEPIC for anything that is over SIP, and also for getting on-the-fly RTP metrics. We have an internal service which we may publish at some time, which is called RTP Insights, which basically goes through the RTP traces for calls and does the analysis, the post analysis to verify what was going on in terms of quality and media establishment. And of course, there's the WebRTC RTC stats, which are exposed, which is an API that is exposed by tools like Chrome, WebRTC internals, or Firefox about WebRTC and Safari in the WebRTC login. What we use also internally is we do end-to-end tests, which is somehow related to the SIP front approach of regression testing. So we have end-to-end tests that are always running in the platform, and they basically simulate the browsers inside the CI environment, and they use the RTC stats metrics to establish that the media was flowing correctly as expected. So they're super useful. Many use the service without knowing them. You can dump all the metrics in one file. You can even now, recently, you can get the audio recordings of everything that was received by the tab or played out by the tab. And you get, probably many are familiar already, you get all them graphed into a human visible and easy to understand graph about what's going on between, in this case, you can see candidate pair, and you can notice something like current round trip time, that's going to be 120 milliseconds, and with a few fluctuations, for example. Some useful Wireshark filters, if you get a big pickup, want to know what's happened, Stein level and turn level, you can use them. They would be in the slides. So in terms of typical issues that we found reported by the customers, timeouts, trying to establish the sessions, high latency in the audio, silence, even though everything looks fine at RTP level, audio disappearing during a call, and obviously classical choppy audio. So timeout, typical case, network unreachable, nothing really new. Many call centers still have the agents all behind NAT, and sometimes they just need to go over turn. And of course, turn over TCP is an option if it's really needed. It's not good for latency. So it could be a way of establishing the call, paying for maybe some audio latency degradation. Or we see DTLS establishment issues depending on implementations. And even there is a trend in call centers where they basically establish one session between an agent and the system, and they keep it for hours, so that they basically just put the agent on a conference with the customer every time it's needed, but the actual call in the browser is still going for hours and hours. And then you need to ensure that if you're using turn, for example, the credentials that typically expire don't, or otherwise you won't have audio anymore. High latency, easy to see in the round trip time graphs. Of course, turnover TCP is a gamble, could be very impactful on latency. When there is silence, sometimes RTP is flowing. There are, 50 packets per second as expected. The RTP streams are there. It's not easy to see what's in there because it's DTLS encrypted, so you cannot just listen to it as easily. But there are some other elements like the audio energy from the RTC stats that can tell you very, very easily whether the decryption of the RTP incoming was actually successful in detecting audio and playing it to the tab, because sometimes it does, but the headphones are disconnected, which is something that happens, and it's a true story. And also, if you extract the audio from WebRTC internals, you would be actually able to listen to what the user of the tab would have heard. So audio energy, also drop packets. If for any reason the RTC peer connection isn't connected correctly with the incoming tracks, there would be no audio played, and packets may be dropped because they are not used. I'm a little bit short of time. Do I have one more minute? And then there's the typical choppy audio, with typically very visible from packet loss. And two of the important metrics in this case is the RTP inbound, which is what the browser received, and remote RTP inbound, which is what the other party claims to have seen. So something that may be useful to see in a working example, simple application using zip.js, connecting to, let's see, WebRTC internals, zip.js, placing a call. Sorry. Placing a call, so maybe it's not audible. It's just, I'm basically playing just a programmable XML on Signalwire, play some music, and you can see, in this case, if I hadn't, you can see a summary of what I was just mentioning. So, summary of the current trip time, 140 milliseconds, bandwidth, and so on. And, I mean, if we just launch a trace just for a few seconds. You can see easily the RTP streams, you can do the analysis, get some useful feedback. Okay. As I mentioned, this is part of a larger presentation that I have, and I think I'm out of time. But if there are any questions.
Thank you, Giacomo. Let's have a question. At least one here.
I have two questions, but I'll ask just the first one. Just a request, why not bring the clue clone to Europe instead of US, because it's kind of a no-go area.
Yeah. I don't know, it would be better also for me.
Area.
I will ask, yes.
Yeah.
Also in Sardinia would be very handy for me.
Okay, that's a question for the organizer. But then Giacomo is going to be around here, so he has a huge experience also with Classivoy, but with WebRTC. So if you need him for sorting out some other questions, please approach him. Now we go quickly to the next speaker, which have